In today's episode, we're going to be talking about isotopes. We're going to be talking about what are they, how they differ from each other, and how they affect the relative atomic mass of the element. Welcome to today's episode. We're going to be talking about what are isotopes, and we'll talk about how do they affect our perspective of relative atomic mass. So if you look at the periodic table that you're using now, you'll see that the relative atomic mass is not a whole number. In your earlier studies, the periodic table you would have been using was much simpler, and the mass numbers for elements in almost every case was a whole number. So let's consider a couple of examples. So sulfur. If you look at your old periodic table, sulfur would have had a mass of 32, and on the periodic table you're using now, it shows us 32.1. Another example, magnesium, was showing us 24 on your old periodic table, the simplified version, but the one that you're using now, it will be 24.3. And if you look across all the elements and compare them, you'll see differences. So why that change? Well, we previously used the mass number, and that was a simple count of the number of particles in an atom's nucleus. And that would work well if all atoms of an element were identical to each other, but they aren't. So how do they differ? How do atoms of the same element differ from each other? And this is a really important thing to remember because it is something that you're going to be asked about. It's something that comes up over and over again, and you really need to understand how they differ. Well, they differ in one thing physically, and that is the number of neutrons in their nuclei, and only that difference. And these different atoms of the same element with different amounts of neutrons are known as isotopes. In fact, isotopes are defined as being atoms of the same element that contain the same number of protons and electrons, but have a different number of neutrons. Note from that definition that the isotopes have the same number of protons as each other, and that makes sense because it's the number of protons that makes the atom a particular element. Every atom of an element has the same number of protons. Also from the definition, we said that all atoms have the same number of electrons. We know that all atoms have the same number of electrons as protons, so therefore all atoms of one element have the same number of electrons too. It's only the number of neutrons that change. So how does this affect their behaviour? Well, very little. One isotope's behaviour is the same chemically as other isotopes of the same element, except that some elements have significantly different radioactive characteristics, but in terms of chemical reactivity and the reactions they undergo, they are identical. If it's only radioactivity, why is it important? Well, it's kind of important to remember that neutrons have mass, and that means that isotopes, because they differ in the number of neutrons, also differ in their mass from each other. And that means that there are atoms of the same element with different relative atomic mass because they have different amounts of neutrons. Coming back to our first point, how do we decide what mass to use as the relative atomic mass of an element? The mass that you see written on the periodic table. We use an average of the atomic masses of the isotopes, and because the isotopes exist in very different relative quantities, that average is weighted by the relative abundance of each isotope. Relative abundance means the proportion of all atoms of an element that happen to be of a particular isotope, and we'll come back to that later. So let's consider an example, one that we mentioned earlier, sulfur. Sulfur has 4 stable isotopes, sulfur 32, sulfur 33, sulfur 34 and sulfur 36. And those isotopes have very varied relative abundance. Almost 95% of all sulfur atoms are sulfur 32. About 4.4% are sulfur 34, about 0.76% are sulfur 33, and less than 0.02% are sulfur 36. So to calculate the relative atomic mass of sulfur, we consider the mass and relative abundance of each isotope, and this gives us a relative atomic mass of 32.1 to 1 decimal place. To watch a short video on how to do the calculation, see the link in the episode details below. One thing you'll notice is that we only included stable isotopes, and that just means those that don't radioactively decay in a short period of time. You might also now be wondering how we find the relative abundance of each isotope. You'll usually be given these if you need to do any calculations, of course, but that doesn't explain where they come from. Well, they're determined using a mass spectrometer. This is done by analysing a representative sample of an element using a mass spectrometer, and the spectrometer separates the different isotopes, and its data analysis enables the user to see the mass and relative abundance of each isotope within the sample. So in order to summarise, let's talk about the important things we need to know about isotopes for your studies at this level. Firstly, you need to know they exist. And you also need to know that they are atoms of the same element, differing only in the number of neutrons in their nuclei, and therefore having different mass from other atoms of the same element. You also need to be aware that some isotopes have radioactive behaviour and others are considered stable. You need to know how to use the mass and relative abundance of an element's isotopes to calculate the element's relative atomic mass. I've included a link to a video that I have showing how to do this, and I've put that link in the show notes. So that's the end of this episode. If you found it useful, please do like it and subscribe it. It really helps to get the podcast out there to more chemistry students too. And do feel free to comment too or to contact me. Best place is Instagram, and you'll find me at Chemistry Made Simple, and there's a link in the show notes, of course. Thank you for listening to this episode. I hope you found it useful, and if you have had value from it, do consider visiting our Patreon community at patreon.com/chemistrymadesimple, where you'll be able to ask deeper questions about this topic and get more support for your studies too. So I look forward to speaking to you again in the next episode, and until then, do look after yourself and goodbye.